In the last episode, I tested the soldering that resulted from using the stencil and the solder jig. So I had a PCB that was I basically designed and had it ordered in. So this time I'm using a little piece of Veroboard. I've created a little circuit with Veroboard. Now I have to solder the two back to back to get this to work. But I'm going to attach this into the port D, which is the top one here as you're looking at this. So as I said the last time, that's ground 3v3 and 5 volts, and then port D 0, 1, 3 to 7. So the circuit, a couple of LEDs and a switch and resistors, is basically using, that's ground on the first, that first pin, and the next pin is 3v3. 5 volts we're not using, and then pin D0 is basically just through an LED and a current limiting resistor and attached down to ground. So this pin D0 is going to be an output pin, and if we set that to a logical high, we're going to light the LED, set it to a logical low, and LED's going out. It's exactly the same circuit as used on pin D1, which again, an LED, forgive my drawing, not an artist, current limiting resistor and through the ground. D2 is going to be different. It's an input pin, so it's going to be through a switch to ground. Now when we connect, this is a momentary switch. When we press the button, this input pin is going to be connected to ground, but when it's open, it's floating, so we want to pull up resistor here, and I think I've made it 10k, and if I change the color of this to be something like that, so that pull-up resistor is just connected straight through to the 3v3 line. You can more or less see that in the circuit here. You can see the way that each of the LEDs is lined up and the switch is lined up on that port, and that's the pull-up resistor and the link through the ground. So that's the circuit, simple. Let's write some code. Now the last time, this is what we had the last time, and that was just basically setting all 8 pins in a row, setting them all high to illuminate all of them. They were all output pins, so we can get rid of all this, like to just cut it all. And in the initialization, the analog select will set everything in, well, the low byte anyway, to be 0. It's all digital pins we're messing with here. And then the tri-state, the last time we would have set everything to be an output, sorry, setting it to 0, 0. These registers are called special function registers in the microchip parlance, and each one of them that has a special function register like that, tri-state D, you can add bits to the end of it and access the individual bits of that register, of that special function register. Now we want to set that bit to be an output, so that's it. Just basically set that one to be an output. We want pin D1, which is on a LED as well, to be an output, and we want pin 2, which is an input, to be binary 1. That is that binary isn't really necessary. The compiler's going to sort out that we're putting a bit value in there, so we can leave that out. It's 6 of one, half a dozen of the other. So now, 2 output pins, 1 input pin. Let's flash the first LED, and we'll do that by setting this delay variable that we used the last time in the macro at the top. We just had that as a delay function looping around on itself. So we'll set that to 0, initialize it to 0, and we'll set the output of that first LED to be high for the moment. And then inside this loop we'll just increment delay and then test it, and if that was the delay we used the last time is 3 FFFF, so if it's equal to that, we'll just reset delay to 0, and we'll set latch D bits, we'll toggle that to the other value. So that should flash the first LED on pin D0. The other LED lets the latch, the lat D register is for output. So when you write to that, you're writing an output value onto the pin. So let's set the second LED, and we want to set that, when you actually read back, it's a different special function register, so it's the port D register. So if we set the bits of that to RD2, so that will read the value from the port RD2, pin D2, and write it to the latch, which is the write for D1. Now, because if we got a pull-up resistor there, by default it's a logical high, we could actually reverse that with a tilde and say that we're going to write the reverse of the read value. So if we read a logical 0 from pin 2, we're going to write a logical 1 to pin 1 and vice versa. So that should compile, which it does. And if we go and connect up power and a picket 3, we can program it. Complete. So if I now just connect up my little pins and power it up, that seems to be working. That's, you might think that's a very simple place to start. It is a very simple place to start. But this cinnamonBun is predominantly about communication over the CAN bus. I'm trying to set this up as a CAN bus node. So these two, the 12 volts input is in the very center pin of this 5, and then the one above and below, directly above and below, are the CAN bus high and low. And those are the ones that it's predominantly interested in communications as a result. So whilst that light in a switch might appear is trivial, at the same time, from simple things, I suppose you could say, very complex creations can be invented. And that was the basis for just that on-off switch is the basis for, or the foundation for Morse code. So I've written that out here. This is in software engineering would be a binary tree. Each step to the left from each node is a dot, and if you move to the right it's a dash. So going to the left here, E is just dot in Morse code. Oops, writing on the wrong layer. E is a dot, I is dot dot, A is dot dash, because you're moving to the left and then moving to the right to get to A. That's just a way of visually showing what the letters are, how they're arranged. Now, the Morse, looking today at Morse code, it's extremely simple. And the reason for that was back in the day, this was read and written by human beings. Right through to the Second World War, when you watch films about the Enigma code and stuff, that like the communications is still using Morse code over broadcast airwaves. So the dot, this duration of a dot, call it D, and this dot is an element. It's one of the primitive elements. There's two primitive elements. There's the dot and then the dash. And I may not have drawn that perfectly to scale, but the dash is 3 times that duration. So a dot is duration and a dash is 3 times that duration. It's as simple as that. In between the spacings you have 3 different spacings. You've got D, which is inter-element. So that's inter-element spacing. So each element is either a dot or a dash. Between them you have to put an inter-element spacing. Like the dash, you've got a 3D spacing. And this was inter-character. So when you finished transmitting a letter, a character, dot A, or dot dash for A, then you had the inter-character spacing. At the end of the word, you had 7. It may not be to scale, but you get the drift. So that's inter-word. So to transmit, say, a simple word like T-H-E, T is dash, so if each of these squares is D, you had a dash which was 3D, and then inter-character spacing which was 3D, and then H is 4 dots. So you had a dot followed by the inter-element, followed by a dot, followed by the inter-element, followed by another dot, followed by the inter-element, followed by another dot, followed by the inter-character, and the last character E was just a dot. So you've just got the dot followed by inter-word. That's the end of the word. That's our T, that's our H, and that's our E. So if you were trying to do this in our little circuit, you could try, and if I had any kind of coordination at all in timing, it would be a long pause, 4 in a row, then a pause, and then another dot, and then a pause, and that would be THE. Obviously my timing isn't going to be brilliant, and probably not understandable by anybody in the real world, but I want to use this as a starting point to try and transmit, just to show the visual whatever of transmitting, and get the microcontroller to do it in code. Now I don't want to do that today because there's a few bits to that I want to get into, so I'll save that for the next time.